Wait 1 second. Let's get rid of this. Okay, what is the internet? Today's inaugural video lecture is about, perhaps appropriately, the internet itself, the medium by means of which I will be communicating with you going forward. We're going to talk about how the internet came about, and we're going to learn about that at multiple levels. The technology itself, of course, but also how that technology reflects and reflected the anxieties, values, and aspirations of the surrounding culture. So many of our descriptions of the internet, like we see early in Neil Stephenson's Mother Earth Motherboard, focus on the internet or describe the internet as a disembodied, placeless, immaterial thing. Wires warp cyberspace, he writes. In the same way, wormholes warp physical space. The 2 points at opposite ends of the wire are, for informational purposes, the same point, even if they are on opposite sides of the planet. Okay, we're going to be thinking about that. The chosen metaphors are important because, as Tung Hui Hu points out, in our descriptions of the internet, often we don't actually talk about the technology at all. We use the technology instead as an occasion to talk about ourselves. So Hu enumerates a whole list of these metaphors, infrastructural metaphors like the information superhighway or a series of tubes, which evokes a sewer, to biological networks like an ecosystem or a rhizome. A rhizome is a kind of plant, which have different valences, that have different connotations. Because it represents a cultural fantasy, Hu writes, it is always more than its present-day technological manifestation. So the internet is never just technological. But to see how this is the case, we're going to have to start by talking a bit about that technological manifestation. How does it work? What is it? So this lecture video is going to talk about the crucial technology of the internet, the central technology that makes the internet, and that is called packet switching. Let's go. Like nuclear energy and rocketry, electronic computers were a World War II innovation. These were not yet consumer products, what we now know as personal computers. Instead, they were serious pieces of infrastructure, often a single computer system that might be the size of an entire room, shared by multiple users via a number of distinct terminals. By the mid-1950s, there were a few clusters of computers, chiefly located at military or government installations. A few corporations that specialized in data processing had some, and research universities had a bunch of them. These computers were increasingly connected together via, quote, networks. But these networks were independent of one another. So what we now know as the internet began as a project of ARPA, the U.S. Government Advanced Research Projects Agency, now called DARPA, where the D stands for defense. The project aimed at coming up with a way of connecting these different insular networks together. And this was difficult because these networks had been designed in as many different ways as there were different networks. So the resulting project, which aimed at, again, bridging the divide, like forming relationships between the networks, was called ARPANET. And so the intellectual groundwork of this system was laid down in the early 1960s, and its first transmissions took place in 1969, shortly after the Doug Engelbart demo you guys have watched was recorded. So the internet is thus 50 years old. The first version of ARPANET was based on a technology called Network Control Protocol, or NCP, which was based on direct and continuous link between different computers. So this was what Engelbart and friends used to link his Palo Alto-based research center to downtown San Francisco, where the demo was given. NCP was clearly quite robust, but the limitations of this approach soon became apparent. Researchers in the early 1960s developed an alternative technique called packet switching. This was basically invented simultaneously in the United States and UK. So instead of a continuous connection, like NCP, that takes up an entire circuit, internet traffic would instead be communicated in what were called packets that vary in size, depending on implementation details, but are generally a little bit more than a kilobyte or 1,000 bytes. So instead of being a continuous flow of data, the message is instead disassembled into pieces and reassembled on the other side. These packets have what are called headers, this is going to be important, which contain metadata on the route the data needs to take to reach its destination, and instructions on how to reassemble it out of these packets on the other side. So this system uses two technologies called Transmission Control Protocol, TCP, that talks about how to take apart and put back together the packets, and Internet Protocol, or IP, that talks about how to bounce the packets around from computer to computer. And so these two things work together. We call them TCP/IP. And this is how the internet works now. And these routes, as we will see, are discovered in real time. Okay, so let's imagine that we have a bunch of different nodes in our network. So we've got and these are all wired together. Like so. So let's imagine now, let me get another marker, that one of these nodes makes a request of another node. Let's say this is the requesting node, filled in blue. In fact, actually, let's number them. Let's give them little blue numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9. Those will be equivalent of their kind of IP addresses, although actual IP addresses are longer than that. And so let's say node 1 wants to request some sort of information from node 9. What route should it take? Now, under a traditional switched circuit system, the kind of way that the telephone system had been set up, a single sort of switchboard would have to decide how to connect them together. But in this distributed system of Internet Protocol, what instead happens is that one sends out a packet, and it sends it out this way and this way. It sends it out to everybody it's in contact with. And then that one passes that along. So it sends it out here and here, and this one does the same thing. And then this one sends it out here, this one sends it out here, and it gets here. And when it gets there, node 9 sends back an acknowledgement. But how does node 9 send it back? Well, in the headers of the packets that were sent out by node 1, each node that passes this along has been amending the headers with the number, with its own address. So, for example, so when 2 retransmitted it to 5, it retransmitted it, but added to the headers. Like so 1 sent it out, and it was like, and its header was like, oh, I'm 1. And then 2 sent it back, and it was like 1, 2. And then 5 sent it on, and it was like 1, 2, 5. Then 6 sent it on, and it was like 1, 2, 5, 6 to 9. So 9, when it wants to send back an acknowledgement, it only sends back an acknowledgement to the first identical request it receives, because that is by definition the fastest route. So it sends it back backwards, 6, 5, 2, 1. So it goes whoop, 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 like that. Sorry about my sound effects. It occurs to me that those are probably really annoying in the video. So the point here is that the fastest route between any two points in the network isn't something that has to be decided by any central authority. It's discovered by the packet switching technology, if that makes sense. What makes possible the switch from centrally organized networks to decentralized networks, and then from there to distributed networks that we see in the drawing from Paul Barron's paper that Tung-Hui Hu talked about. Now, the traditional story, and there is some truth to it, was that the intentions of this packet-switched model was to make the communications network resilient against nuclear attack. This was the Cold War. Paul Barron's essay, from which this image comes from, is explicit that any new communications network needs to assume that any given node could be destroyed, presumably by nuclear attack. In fact, the way people spoke during the Cold War, the assumption was that the kinds of places where such crucial infrastructure was being built, places like Washington, D.C., New York City, Chicago, Boston, the Bay Area, Los Angeles, Seattle, were precisely the kinds of places that were most likely to be targeted in a nuclear attack. So even a decentralized system would still be too centralized for the needs of withstanding such an attack and maintaining communication afterwards. But a distributed network would be different. If any node goes offline, a distributed network would have sufficient sufficient redundancy for a packet switch network to just route around it. But as Tung-Hui Hu points out, this idealized vision of the internet as a distributed, self-routing, self-healing network was not actually what we built. Because of physical facts like the submarine cables that Neil Stephenson talks about, or legal facts like the difficulty of securing long rights of way to lay fiber optic cable across the country, what we actually built and what we actually use, even in the United States, where the internet is perhaps the most robust it is anywhere in the world, is really more of a decentralized network than a distributed network, using Barron's terminology. What we have is a network of networks still. Each local network, or subnet, would now be connected to a router, also called a gateway. The router is a specialized computer that only serves a networking function. It would assign each member of its own network a local IP address. But the gateway would also connect to a larger internet, and it would have its own IP address within that scope. And its role would be to route, hence router, packets to and from the computers that it supervised. So, if you have a broadband internet connection, you likely have a router in your house. That router connects to your ISP, Comcast, Verizon, or Charter, or whomever, where it is nested under yet another router, which is in turn connected to the global internet. So your own router administers the subnet in your house. So in my house, that means it connects my laptop and my wife's laptop, both our cell phones, our printer, an Apple TV, this thing we use to stream music over Wi-Fi. You get the idea. You probably have a similar collection of things in your house. Maybe you've got some like internet connected light bulbs or like a smart fridge. I don't know. So my router assigns each of these internet connected things an IP address. So that IP address, it's 4 numbers separated by dots. The numbers are between 0 and 255. Now, local addresses on subnets all use the same handful of IP address ranges. The most popular are 10.x.x.x and 192.168.x.x. So because these are supposed to be used within private networks, in principle, they should never overlap. So my router's IP address locally is 192.168.1.1, and it's entirely possible that yours is too, but it doesn't matter because they're on different subnets. Our routers also have outward-facing IP addresses as well, as part of the subnet that they are part of at our ISPs. Those IP addresses need to be distinct among subscribers to that ISP. And then our ISPs are all part of the network of networks that exist alongside university, governmental, and corporate networks. Those, similarly, all need to be unique in that context. Whew. Okay, so when you type a URL into your browser window, what happens exactly? The first step is that your browser reaches out to something called a domain name server, or DNS. The DNS is like a phone book, but I'm guessing few of you really use a phone book, especially the younger people. So the DNS system is more like Yelp. Okay, let's say I want to order delivery from my favorite Chinese restaurant on the north side, Silver Seafood. I should have their number in my phone, but I don't. So I ask Yelp for the number, and then I can dial that and reach them. DNS works the same way. You use it to look up the addresses of things that you have the name of. So DNS servers talk to one another, gradually propagating up-to-date information about where various resources are hosted. So if we type a URL like www.ccc.edu into a browser, the browser asks a domain name server, likely one maintained by your ISP, what the corresponding IP address of the web server for www.ccc.edu is, and it returns an IP address. In this case, that's 52.44.45.178. And then your computer sends out a packet with the request to load a site. This is called a synchronization packet, or SYN. SYN. That packet propagates out from router to router, taking a number of hops, like we described above. Each hop adds its information to the packet header. When the server receives the request, it sends a synchronization acknowledgement packet, SYN-ACK, back, using the header information as a kind of breadcrumb trail to find its way back to the original sender. So again, the fastest path may not be what you would logically think of as the most direct path, and it might change depending on network conditions. The path it takes today might not be the path it takes tomorrow. But the first packet to reach the server is the one it responds to. That's the one that got there first. That must be the closest route. So once this returns to the original host, it sends a third packet back along the same route called an ACK packet, and this completes what's called a TCP/IP handshake. So then the server breaks down the data you asked for into a bunch of packets, each carefully numbered in their headers, and sends them all back to your computer along the path negotiated in the initial handshake. So once your computer acknowledges that it has received them all, they do another handshake. This one starts with a FIN, or finish code, and they end the session. So now, using a Unix utility called traceroute, we can inspect these TCP/IP headers. This shows us the hops to the City College website. The first of these hops is my home router, which I recognize from its use of the private block of IP addresses starting with 192.168. The next two have no identifying information I could discern. I'm guessing they're DNS servers. But then we get into Comcast stuff. They have helpfully included geographic identifiers in their URLs, probably to help them troubleshoot issues that pop up. Looking closely at the URL, we see a Comcast installation in Elmhurst, that's like just south of O'Hare, I think, another in Chicago, and still a third located at 350 East Cermak, the one-time largest data center in the world, which is located just east of Chinatown. Our request bounces around in that data center for a few hops before heading to Virginia, which is where I infer CCC's web host is located. The longest one of these hops takes just over 16 milliseconds. So I think the takeaway from this is basically the same one proposed by Hu, and maybe Stevenson too. No matter how much our use of the internet or various cloud resources try to conceal from us the physical reality of what we're doing, there remains an underlying geography to it. There are buildings full of computers connected by wires that we are using. When I keep my files backed up on Apple's iCloud, that just means I'm saving a copy of them in Catawba County, North Carolina, right here off State Route 321, in this gleaming white building next to a giant solar panel installation. Looks like there's a Hardee's just up the road, but I bet you can get better barbecue elsewhere.